Welcome to this complete guide on software engineering. Whether you're a beginner or revising for your exams, this video will take you step by step through the fundamentals. So, grab your notebook and let's get started. To understand software engineering, we first need to distinguish between a program and software. A program is a set of instructions that performs a specific task. Think of it like a simple recipe for a single dish. A calculator app, for instance, is a program designed to perform mathematical calculations. It's focused and self-contained. But software is much more. It's an entire system, like a fully staffed restaurant kitchen with many chefs, recipes, and supply chains all working in concert. Software is a collection of numerous programs, configuration data, and documentation, all intricately woven together to create a complex, functional whole. Your computer's operating system is a perfect example, a vast suite of software managing everything from your mouse clicks to your internet connection. It's this immense scale and complexity that necessitates a formal, structured approach to its creation. This is where software engineering comes in. The word engineering is crucial. It implies a systematic, disciplined, and quantifiable approach. Anyone can stack a few bricks, but to build a skyscraper that's safe and will last for centuries, you need civil engineers. Similarly, to build robust, large-scale software, you need software engineers. This discipline covers the entire life cycle of a software product. It begins long before any code is written, with requirements analysis to understand user needs. Then comes system design, creating the architectural blueprint. Only then does development, the actual coding, begin. Afterwards, the software undergoes rigorous testing to find and fix defects before it's deployed to users. But the job isn't over. The final and often longest phase is maintenance, which involves fixing bugs, adding features, and adapting the software to changing needs over its entire lifespan. The ultimate goal is to produce high-quality software, but high quality is more than just it works. It's defined by several key attributes. It must be reliable and robust, functioning correctly without crashing. It should be efficient, using system resources wisely. Crucially, it must be maintainable, so that it's easy to fix and update in the future. It also needs to be secure, protecting user data from threats, and usable, providing an intuitive experience for the end user. Software engineering provides the frameworks to achieve this quality while balancing the classic project constraints: scope, time, and budget. Delivering a product that meets all requirements on schedule and within budget is the hallmark of a successful project. Software products themselves come in many forms. The two main categories are generic and customized. Generic products or off-the-shelf software are developed for a broad market like Microsoft Office or Adobe Photoshop. The development company decides on the features and sells the same product to many customers. In contrast, customized products are commissioned by a specific client for their unique needs, like a proprietary trading platform for a bank or a company's internal inventory system. Beyond these, there are countless other types, from embedded systems running inside your car to the web-based systems and mobile applications we use every day. A complete software product is also more than just the executable program. A software system consists of several critical parts working together. You have the programs themselves, the code that runs on the computer, but you also have configuration files which allow the software's behavior to be changed without rewriting code, making it flexible. Then there's system documentation, which includes architectural diagrams and design notes written for other engineers. This is the map that allows future developers to maintain and extend the software. Finally, you have user documentation like manuals and help guides written for the end user. All these components are essential for a successful and sustainable system. To manage the creation of these complex systems, engineers rely on development methodologies. Historically, the waterfall model was common, a linear approach where each phase must be completed before the next begins. This can work for projects with stable, well-understood requirements. However, today most teams use Agile methodologies. Agile is an iterative approach that emphasizes flexibility and customer collaboration. Work is broken into small cycles called sprints, with the team delivering a working piece of the software at the end of each cycle. This allows for continuous feedback and makes it easier to adapt to change, which is a constant in the world of software. When building software, having a roadmap is essential. These roadmaps are known as software process models, and they provide a structured framework for the entire development lifecycle. Let's begin with the classic, the waterfall model, which is the oldest and most straightforward approach. It follows a strict linear sequence of stages, much like a waterfall cascading downwards. Imagine building a house. First you create a detailed blueprint. That's requirements analysis. Then you lay the foundation and frame the structure. That's system design. Next comes the construction, implementation. After that, inspectors check everything. That's testing. Finally you move in, deployment, and then you handle upkeep, maintenance. Each phase must be fully completed before the next one can begin. This sequential flow is its defining characteristic. However, its limitation is rigidity. In the real world, requirements are rarely static. A client might realize they want an extra window after the walls are already up. In the waterfall model, once a stage is completed, going back is very difficult and incredibly costly. This means you might spend months or even years building a product, only to find at the very end that it doesn't meet the user's actual needs, which may have evolved over time. In contrast, the evolutionary model builds systems through repeated cycles, with each version refined based on user feedback. Instead of building the entire system at once, this model delivers a working version early and then improves it over time. This approach has two main flavors: prototyping and incremental development. With prototyping, the goal is to quickly build a mock-up or a functional but incomplete version of the system. This prototype is shown to users to gather immediate feedback on the user interface and functionality. It helps answer the critical question, are we building the right thing, before significant resources are invested. The incremental approach, on the other hand, breaks the project into smaller, manageable chunks. Each increment adds a new piece of functionality, allowing a usable product to be delivered much sooner, with value being added continuously. This iterative philosophy is the heart of modern agile development, which emphasizes flexibility, customer collaboration, and rapid delivery. Agile isn't just one model, it's a mindset captured in the Agile Manifesto. It values individuals and interactions over rigid processes and responding to change over following a strict plan. This philosophy is put into practice through frameworks like Scrum and Kanban. In Scrum, work is broken down into short cycles called sprints, typically lasting 2 to 4 weeks. Each sprint aims to deliver a potentially shippable increment of the product. Daily stand-up meetings keep the team synchronized, and regular reviews with stakeholders ensure the project stays aligned with customer needs. This makes Agile perfect for projects where requirements are expected to change. Component-based engineering focuses on reusing existing software components, saving both time and cost. Think of it like building with Lego bricks instead of making every single piece from scratch. Software is assembled from pre-built, reusable, and self-contained units called components. A component could be anything from a simple user interface button to a complex payment processing service or a mapping API like Google Maps. By integrating these pre-tested, reliable components, development teams can significantly accelerate the development process, reduce costs, and improve the overall quality and consistency of their software. For large, complex projects, the spiral model combines iterative development with systematic risk management. It visualizes the process as a spiral, with each loop representing a phase. It elegantly merges the iterative nature of the evolutionary model with the controlled, systematic approach of the waterfall model. Its key differentiator is an explicit focus on risk. Each loop of the spiral progresses through 4 quadrants, determining objectives, identifying and analyzing risks, developing the next version, and planning the subsequent loop. This mandatory risk analysis at every iteration forces the team to proactively address potential problems before they become crises. This makes the spiral model an excellent choice for mission-critical systems like aerospace software or large-scale financial platforms, where failure is not an option. Ultimately, there is no single best software process model. The ideal choice depends entirely on the project's unique characteristics, its scale, complexity, budget, and the clarity of its requirements. Many modern teams even adopt a hybrid approach, blending the structure of one model with the flexibility of another to create a custom process that best fits their needs. The key is to choose a model that provides the right balance of structure and adaptability to guide the project to a successful conclusion. The journey of creating any software begins with requirement engineering. This is the foundational process of discovering, analyzing, and documenting what the system must do. Getting this right is paramount, as a misunderstanding here is far cheaper to fix than flawed code later. The process involves feasibility studies to assess viability, elicitation through interviews and workshops to draw out customer needs, and documenting everything in a formal specification. Finally, these requirements are validated with stakeholders to ensure everyone shares the same vision before development begins. Once we know the system should do, software design determines it will do it. This is the blueprint phase, translating requirements into a concrete technical plan. It starts with architectural design, defining the high-level structure and how major components interact. Then, detailed design fleshes out the specifics of each component, its internal logic, and data structures. A critical part of this is user interface and experience design, which ensures the software is not just powerful, but also intuitive and accessible for its users. With the software being built, we enter the validation phase, a rigorous process of testing to ensure the product meets its requirements and satisfies user needs. This involves both verification, are we building the product right, and validation, are we building the right product? Testing occurs at multiple levels. Developers perform unit testing on individual code components. Integration testing ensures these components work together. Finally, acceptance testing involves the customer, who confirms the system is ready for deployment, ensuring quality and reliability before it goes live. A project isn't finished at delivery, it's just beginning its longest phase, evolution. Software is not static, it must continuously adapt to remain useful. This evolution is driven by many factors. Bugs discovered after release need fixing. The system must be updated for new operating systems or hardware. Most importantly, business needs change and user feedback provides a constant stream of ideas for new features and improvements. This ongoing process of maintenance and enhancement ensures the software continues to provide value long after its initial release. In summary, we have 4 fundamental activities: specification, development, validation, and evolution. These are not always rigid, sequential steps. In modern methodologies like Agile, these activities occur in rapid, overlapping cycles. A team might specify, build, and validate a small feature in just a few weeks, then repeat the process. This iterative approach allows for flexibility and continuous improvement, forming the core loop of modern software engineering that delivers value to users quickly and consistently. So that's a complete overview of software engineering, from the basics and process models to requirement engineering and agile practices. If you found this video helpful, don't forget to like, share, and subscribe for more educational content.